Hello, welcome to lesson 24, electromagnetic waves. All right, so I'm gonna let you guys read through this part so that you guys can do that part. And I'll kind of skip to the ones that's gonna be a little bit tougher to comprehend. So, principles of electromagnetism. So, a guy named Maxwell. So you can see the name up here, right? James Clerk Maxwell. Um, he was really a brilliant mathematician. He took the ideas of Faraday and some of the others that we learned from earlier and started making this into a theory of light, right? Like how does magnetism have anything to do with light? So what he did is he started learning about the things that we've been learning about in previous lessons here, and about um, Oersted and Ampere and Faraday, and took this idea that a constant electric current in a conductor induces a uniform constant magnetic field that circles the conductor. The electric current and magnetic field are perpendicular. Okay, so that sounds confusing, but what that is, right, is that if you had current going through a wire, or electrons, sorry, then it's going to create a magnetic field going around that guy, right? Like we've talked a lot about that now. So that's all he was really saying there. And then the next part here, when a conductor moves through a perpendicular magnetic field, a uniform constant current is induced in the conductor. Well, that one. So that one is talking about our last unit, right? This is the generator effect. When you move a wire in a magnetic field, right? You have a changing magnetic field then when you're moving that wire in the magnetic field. And a changing magnetic field is going to produce a current going through a wire, right? So that was just everything from last lesson. All right, so then what this guy Maxwell did was he started saying, well, does this happen only in conductors, or does it happen in any object? So he did a few experiments there and found that it actually happens in insulators as well. So then that kind of opened the door to say, well, maybe this sort of thing happens in just open space, right? It can have this process could happen in a vacuum of space. All right, so Maxwell, since he figured out this, it's not just in conductors. He changed it to be more field, like more about fields in general. So he said he changed Ampere's principle of magnetic induction to a changing electric field in space will generate a changing magnetic field. Oh, sorry, a changing electric field in space will generate a changing magnetic field that is perpendicular to the electric field. Okay, so it's just kind of fields. One field will create another field, right? And then the other part of it, he says, well, a changing magnetic field in space, so it doesn't have to be in a conductor, will generate a changing electric field, and it's going to be perpendicular to the magnetic field. All right, so what that means is really this picture. So what this picture is showing is that if you have some, and it's always going to start with some charged particle accelerating, so you get some charged particle accelerates upward like that, or downward, doesn't matter. What that's going to do is that's going to create a magnetic field that starts to circle around it, right? That's the same thing as a current going through a wire, right? It creates a magnetic field. But they said, well, that's circular motion happening, right? You've got a changing magnetic field going around that accelerating charge. What that's going to do is that's going to create a changing electric field. So we got an electric field circling that. Well, he said, well, a changing electric field creates a changing magnetic field, and so on, right? You get this chain of events that's happening, which is pretty neat because this is what light is. That's all light is. It's a changing electric field, and then a changing magnetic field, then a changing electric field, and then a changing magnetic field, and just on and on and on. And this process of those fields changing back and forth, that's happening at the speed of light, right? That is light. This is what light actually is. Okay. So another way of drawing this, and actually to tell you the truth, a more common way of drawing it is like this. And this is just showing again where you've got your electric field as like a maximum, and then it passes through a point, and then it's going to come to a minimum, a maximum, a minimum, and then you've got your magnetic field doing the same thing, but it's always going to be perpendicular. They're always perpendicular to each other, those two fields. Okay, so just another way of looking at it. Okay, so yeah. All right, so like I was saying in the last part there, so let's just go through some of his predictions that he made with this theory. He said the primary cause of all electromagnetic waves is an accelerating electric charge. Put a star by that. That's an important concept. That is how all of this gets going. That's how you make an like an electromagnetic wave. It has to be accelerating, right? So if a question says you've got some electric charge traveling at uniform motion, they're trying to trick you. It's not going to create an electromagnetic wave. It has to be an accelerating electric charge, okay? As an electric charge oscillates / accelerates, electric energy will be lost, and an equivalent amount of energy will be radiated outward in the form of oscillating electric and magnetic fields. All right, so what we're really kind of talking about here too. Let me find a little place to draw this. If you had something simple like a hydrogen atom, so you got one proton and one electron, right? What we're saying here is that if for any of you guys that have taken chemistry at all, or remember, back to Science 9 and Science 10, there's these things called orbits, right? So the higher up the orbit is, it's just the bigger the energy gap, right? Or the bigger the energy. So what'll happen? Just erase the top part of this. What happens in atoms is that, let's say this electron was sitting here, right? Well, then it can jump up. If you give it enough energy by a few different ways, you can give it like through electricity or something, but you give enough energy to jump up to the next energy level, it'll jump up there and it'll hang out there for a little bit, and then it'll spontaneously jump back down again. Okay, well, that jumping back down again, it's going to emit energy. It's going to emit energy because it lost that energy, right? That energy has to go somewhere. That energy, that accelerating electric charge, is what starts our electromagnetic wave, right? Which is just that series of electric field, magnetic field, right? But it's that process of that electron just jumping down from one energy level to the next. So that's really kind of what our first thing is talking about here, if you wanted just a bit more explanation on that one. So as an electric charge oscillates or accelerates, electrical energy will be lost, right? So energy is lost when that electron jumps back down, and an equivalent amount of energy will be radiated outward. So the energy being radiated outward there is the same as the energy lost due to that electron jumping back down. Okay, so that's all that means. Okay, number 2. When the electric charge is accelerated in periodic motion, the frequency of oscillation of the charge will correspond exactly to the frequency of the electromagnetic wave. Well, that really means if you had a charge that was going up and you oscillated it back and forth, back and forth, back and forth, that would be the same as the wave that was produced. Okay? All electromagnetic waves will travel at a speed of, and this is what he said. He said this large number, which is actually pretty amazing because he came up with this large number all from the math. Remember, he was like a brilliant mathematician. And this number is quite close to what they actually observed later on as being 3 times 10 to the 8 meters per second, right? The speed of light. And he also said it's going to obey the universal wave equation of C is equal to frequency times wavelength. Okay? The next one, the oscillating electric and magnetic fields are always perpendicular to each other, right? And perpendicular to the direction of propagation of the wave. Well, what that means for the last part is that one is going, so if this is the electric field in that direction, this is the magnetic field in that direction, then the wave, the direction of it would always be going perpendicular to both of them. You know what, it might be better to actually show you this picture again. So if you can see this one, right, if these guys are, this one and this one are perpendicular to each other, the motion of this wave is perpendicular to both of them, right? That's the direction that this thing is going, like out of the page this way, or like sideways in that one. So it's like if they're going in the third dimension there. Hopefully that made sense. Okay. Okay. Next one is just saying that if this is true, then we should see all the same sorts of stuff we see with waves that they think light is at this time, right? We should see interference, right, that we've talked about with light. We should see diffraction, we should see refraction, and we should see polarization, right, all those light waves lining up perfectly. And that would make sense, they would, right? Because if you've got something that looks like this as a wave, or as like our model for light, then this too, if this all hit water, let's say, like a lake, that would all polarize a bunch of those light rays into the same direction. So that would polarize it. All right. Oh yeah, and then the last one. Electromagnetic waves should produce pressure when they came in contact with the surface. You know what? I'm not exactly sure why he made that prediction for that one. I'm thinking it was in the math. Like I was telling the other students that Maxwell is actually someone you can take like an entire course on, like learn how he came up with all of this, like brilliant mathematician again. But later on, when we get into quantum mechanics, we're going to talk a bit more about why this actually is true as well, looking at it from a quantum mechanics point of view. All right, so thing is, Maxwell wasn't like he was a brilliant theoretician, but he wasn't really a great research scientist, right? So he wasn't great at setting up experiments for the most part. So he wasn't able to really prove his own theories, is the idea there. But a guy named Henrik Hertz, which comes up a lot, he was a great research scientist. He set up an experiment right here. This is the way this experiment works. Is you can see right there, there's a gap between those. Really, all he did is he had really high voltage between those two. Then he set up another part of the experiment on this side where there was another gap. Right, you see the gap right there. What would happen, he hoped, is that if you shoot a spark down from one to the other, well, that spark is a changing an accelerating electric particle, right? You'd have electrons jumping across, so they'd be accelerating. They should produce a wave, right? They should produce an electromagnetic wave. And if the electromagnetic field, part of the wave, lines up perfectly with this side, that should induce a current in this coil, and that is actually what you see. And then on that note, what he did to see if it actually looks like Maxwell's wave is he turned this whole apparatus 90 degrees so that it would have been the magnetic wave that would have been lined up with that. Then it didn't do anything. It wouldn't create a spark. So that, and then he turned it 90 degrees again, so it was turned right upside down, so 180 degrees from the beginning, and then you saw the spark again. So it was really good proof that the wave actually did look exactly like the wave that Maxwell was predicting. And then the other thing is that he had it set up in such a precise way that he was able to measure the actual time that these guys actually, the sparks took place. So it would be this spark, and then like slightly after it, this spark would come. And if you did the math on the distance that was between them, right? So just velocity is equal to distance over time. The velocity actually happened at the speed of light. So that was also good proof, right? That this wave that was coming through here was actually light. It was just light you couldn't see. So it was part of the electromagnetic spectrum, but they didn't really have a word for that at that time. So electromagnetic waves are light. That's what it is. So you guys did this way back in Science 9. You talked about electromagnetic radiation. And then, sorry, the last part here, that his prediction about electromagnetic radiation exerting pressure was discovered as well. So that was more proof that was the case. All right, the electromagnetic spectrum. So we've seen this picture before. Before we didn't really have to memorize it, but now we do. We have to memorize some of it. So you guys are going to be responsible for knowing these different names, these different sections of the electromagnetic spectrum. So there's our visible light, there's our infrared, our ultraviolet, X-rays, gamma rays, etc. And all that's happening here is that if you go this way, you're getting higher energy, so high frequency and low wavelength and small wavelength radiation. And if you go this way, you're getting like, the radio waves. Some of these waves can be the size of like the Earth if you go far enough this direction, right? They have a huge wavelength. And then some of them have pretty short, like a microwave is a pretty short wavelength, but not that short. It's not like an X-ray or something, right? Yeah, so 10 to the negative 2, right? Or this one, right? You can see this one has a wavelength of 1 meter is what a TV wave would look like, right? Yeah, and you can see the frequencies on the top and the wavelengths on the bottom there. Okay. So, like I said, you're going to be responsible for knowing some of those, or all of them, knowing how each type of radiation is produced and detected. That's on the next page. And then using the universal wave equation, so C is equal to wavelength times frequency, to calculate wavelengths or frequencies, okay? So this page, I'm going to let you guys read through these ones. So like I said, these different types, and then know, what produces them, and then where you'll find them. Is going to be in that one. I'll kind of explain maybe some of these a little bit though. So higher energy transitions of outer electrons in atoms. That's exactly that picture that I was showing before, right? So if you have a proton, all that's talking about is the electron jumping down to another orbit. So that's what it means. So if you say higher energy transitions of outer electrons, so the outer electrons are the ones on the outside, here. Right? So that's what that's talking about. And then transitions of inner electrons, yada yada, and then yeah. So you guys can read through those. This is going to be a good aid for you guys because it's going to remind you what it is you actually have to memorize. So you need to remember that 700 nanometers is about what the red wavelength is, and that 400 nanometers is about what the violet end of the visible spectrum is, right? So this is the visible spectrum of light. You need to know 700 to 400. And then just remember Roy G. Biv, right? That's just your colors of the rainbow, right? The colors of the visible light spectrum. So you don't need to know that, exactly the wavelength of yellow, green, blue, whatever. But just need to know that these all fall within that range. And that maybe blue is going to be a shorter wavelength than orange would be, or yellow, or something like that, right? Okay. And then the next part here, you're going to need to know the frequency or wavelength, it doesn't matter which one, but frequency is an easy one to do. TV, microwave, yada yada, all these ones, right? And just notice when you're memorizing these that it goes up by, so it's 10 to the power of 8, 10 to the power of 10, 10 to the power of 12, right? They're going up by 2s. So it goes 10 to the power of 8, 10 to the power of 20. And then a good way to memorize it is just memorize the order that these go in. It's not a great one for making up an acronym. If you can think of an acronym, then go for it. Yeah, hopefully you guys are good with that one. And then that's it. So just do the hand-in assignment. There is no practice problems for this one. This is really pretty much mostly theory stuff. Remember, there is a key on the website as well.